Hey guys, how's it going? So in this question what we're going to do is we're going to basically build some intuition of how to use mathematical expressions and equations to solve physical problems. To do that, we're going to look at a basic collision problem. So let's see. In this setup, we have two bodies. You can imagine them as two balls, let's say, that are being thrown up simultaneously at the same moment in time. The first body is thrown from a height of 1 meter above the ground or above some reference point with a velocity of 10 meters per second. And the second body is thrown from the ground or from some reference point at least with a velocity of 12 meters per second. So there's three questions that we want to be able to answer. We want to answer first, when in time will the bodies collide with one another? Second, we want to answer where, that is, where in space will they collide? And third, we want to know what the velocities will be at the moment of the collision. To simplify things, of course, we're making a few assumptions. We're assuming, first of all, that there's only gravity at play, and we're assuming that the two objects are being thrown or they're moving in the same direction. We have also an animation of what this should look like more or less, just to give you an idea. We have, first of all, our blue object, which starts off at a height of 1 meter above the red object. Remember, the blue object starts off with a velocity of 10 meters per second and the red object with a velocity of 12 meters per second. And in the animation, we're showing as though the objects move past one another. They're able to move through one another. Of course, in reality, if these were actual objects, then they would collide and bounce off one another. But we don't want to worry about that for now. The main point to realize is that even though they start off separated by some distance, then at some moment in time and at some height, they catch up with one another and they overlap. And of course, the reason that they're able to overlap is because even though the blue object begins a little bit higher up than the red one, it has a little bit of a head start, the red object is faster than the blue one, and that's how it's able to catch up and collide or meet the blue object. So to actually begin solving this problem, we need to know two equations. These two equations we should have memorized by now. The first one is describing the location of an object in time, and that's given that we know what its initial position is and what its initial velocity is, and we know what the acceleration on the object is. That is to say, we have the equation that y parentheses t equals y naught plus v naught t plus 1/2 at squared. So we have the position as some function of time on the left-hand side, and on the right-hand side we have the initial position plus the initial velocity times whatever time we're looking at, plus 1/2 times the acceleration times the time squared. The second equation that we need to know is just that v sub t, the velocity as at a moment in time, is equal to the initial velocity plus the acceleration times the time measured from the initial moment. That is v parentheses t equals v naught plus at. So to begin, let's start off by writing the various parameters for each object, for each body. Let's start off with the blue object, the blue body, and we'll write that in blue just to clarify. So we have its initial position is 1 meter above the ground or above the reference point. Of course, we're going to be taking up as the positive direction. And so y sub 0, the initial position, is just going to be plus 1. The initial velocity, we're told, is plus 10 meters per second up. And gravity, which is going to be the acceleration, the only acceleration in this case, is approximately minus 10 meters per second squared. Likewise, we can do the same thing for the red object. So when we actually plug in the values, we have y naught equals 0. It's starting off at the ground. We have v naught equals plus 12. And again, we have g, which is the acceleration due to gravity, is minus 10. It's approximately minus 10. So now we can just actually plug in these individual parameters into the actual general equation. So let's start off with the blue object. So we know that its position as a function of time, that is its position at any moment in time, is going to be equal to 1 plus 10 times t minus 5 times t squared. We plugged in 10 for v naught, 1 for y naught, and then 1/2 times minus 10 is minus 5. And just to do a quick sanity check, a quick logic check, we can see that, let's say we look at the time when t equals 0, then we just have 1 plus 10 times 0 minus 5 times 0 squared, which is 1, plus 0, minus 0, or 1. So that makes sense. And then you can actually do a simulation. You can run a simulation by plugging in various different values of t, starting off, of course, from t equals 0. And then you'll see what the position is of that object at various moments in time. For example, if you plugged in that t was equal to 2.16, then the position would be minus 0.77. Now, of course, if you literally imagine that the ground is the ground, then this would mean that it's somehow sunk below the ground. If you just imagine that the ground is just some reference point, then it's easier to imagine how the position is below that reference point. But again, the point is that we can plug in various values for t and get the position. Now we just do the same thing for the red object. So if we plug in the actual values for that object, we have that y parentheses t equals 0 plus 12t minus 5t squared. Again, y0 for the red object is 0, v0 is 12, and of course 1/2 times minus 10 is minus 5. Likewise, we can also plug in different values for t and get the position of the red object in different moments in time. But the question wants us to find what the time is during the collision. So if we run the animation again, we can see that the red object basically catches up to the blue object. In other words, they both have the same value for y parentheses t. That is to say, we can make 1 plus 10 times t minus 5 times t squared, which describes the position of the blue object, equal to 0 plus 12 times t minus 5 times t squared, which describes the position of the red object. And we want to solve for time, we want to solve for t, so we want to basically isolate t on one side and any constant terms or other terms on the other side. So first of all, we can obviously get rid of the 5t squareds, because if you add 5t squared to both sides, then it just cancels. So now we just want to put the t terms on one side. So let's see, 12t minus 10t gives us 2t. And then 1 minus 0 is obviously 1. And so we get 1 equals 2t, or t equals 0.5. So that means that the time during the collision, the time when the two objects meet one another or collide or occupy the same location in space, let's say, is going to be when t equals 0.5 seconds. So that answers the first question. The second question is, of course, where will they collide? Where in space will they collide with one another? And the convenient thing is we can plug in this value of t into either equation, into the blue equation or the red equation. And of course, we should have the same result. That's the whole basis of how we solved the first part. So let's start off with the blue equation. We'll plug in t equals 0.5. So let's see, we have on the left-hand side, we have, of course, y at the time t equals 0.5 equals, and then on the right-hand side, we have 1 plus 10 times 1/2 minus 5 times, well, let's see, what's 1/2 squared? It's just 1/4. So minus 5 times 1/4. All of that, when you evaluate, gives you 4.75. In other words, that the height above, of course, the ground above the reference point is 4.75 meters above that reference point. Let's just check that we have the same result for the red equation, for the position of the red object. So let's see, 0 plus 12 times 1/2 minus 5 again times 1/2 squared is 5 times 1/4. When you actually plug that in, you get, again, 4.75. So we've solved the second question now. We've solved where will they collide. And last, we want to be able to answer what will the velocities be during the collision. And in this case, we obviously want to know what their velocities are individually, because it won't necessarily be the same velocities for both objects. So to solve that, we're going to use our other equation, the velocity equation, as a function of time. And again, let's start off with the blue object. Well, all we have to do is we have to plug in our value of t, and we know what the value of v0 and a are. So let's see, we have the initial velocity is 10, so 10, and then a is minus 10 times t. So the equation is 10 minus 10t. And the time of the collision, again, is going to be 0.5. So we essentially have 10 minus 10 times 1/2, which is just 10 minus 5, or 5 meters per second. So that is the velocity of the blue object at the moment of the collision. Now we have to check what the velocity is of the red object. So let's see. In this case, we have v0 is equal to 12, and again, a is minus 10. So 12 minus 10 times 1/2 is the same as 12 minus 5, which gives us 7. 7 meters per second. So we can see that the red object is obviously moving a little bit faster than the blue object. And actually, if you'll note, the initial difference in the velocities was 2 meters per second, right? The first one started off at 10 meters per second and the second at 12 meters per second. And they're thrown at the same moment in time. And the only force that's slowing them down is, of course, gravity. And so it makes sense now that at the moment of the collision, the difference in the velocities will still be 2 meters per second. The red object is still 2 meters per second faster than the blue object. Now, of course, there's many more things that you could be asked to solve when dealing with a question like this. And that, of course, depends on different assumptions you're making about the types of collision, about the types of objects, various things. But again, in this question, we just want to build some intuition of how to use the different mathematical expressions or physical equations to solve these kinds of problems. Anyway, that's going to do it for this video. I hope everything made sense and was clear. And with that said, let's move on to the next problem.